Welcome back to this course on multi-core architectures. The topic of this module is memory consistency. Informally, the memory consistency model defines the order of reads and writes to different memory locations. This module consists of 3 lessons. In the first lesson, I will introduce and motivate memory consistency. In the second lesson, I will describe an intuitive memory consistency model for multiprocessors called sequential consistency. Sequential consistency, however, restricts many common hardware and compiler optimizations. To alleviate this problem, many current multiprocessors support relaxed consistency models, some of which I will describe in the third lesson. This lesson is mainly based on section 5.6 of the textbook. Some slides and figures have been based on other sources. Let's start by describing the issue, the memory consistency issue. This example we have seen several times before. 2 threads, T0 and T1, synchronize using a busy waiting loop. Thread T0 first sets A to 1 and then sets a flag, and thread T2 waits until the flag has been set and then prints A. Clearly, the purpose of this program is to print the value 1. However, there is an implicit assumption the programmer made. The programmer implicitly assumed that the writes to A and flag occur in the order specified by each thread. In other words, he or she assumed that the writes occur in thread order. However, if thread T2 observes or sees the write to flag before it observes the write to A, then it will print the value 0, which is not what the programmer intended. Can this happen? Are writes not always executed in thread order? Unfortunately, the answer is yes. Yes, this can happen. Recall from the memory hierarchy module that a core may feature a merging write buffer. On the next slide, I will show that a merging write buffer may change the order of writes. A brief recap that explains why a merging write buffer may change the order of writes. Suppose the processor or core issues consecutively write foo, write A, write flag, and finally write bar. Also assume that these 4 variables are allocated in memory, typically by the compiler, like this. Foo and flag are placed together in the memory block that starts at address 200, and A and bar are placed together in the block that starts at address 400. If the core supports a non-merging write buffer, each write buffer entry will be a single word and consist of an address, a valid bit, and the data word to be written, as shown here. If the core now writes foo, it will be placed in the first entry of the write buffer. Then the core writes A, which will be placed in the second entry. After that, the core writes flag, which will be placed in the third entry of the write buffer. And finally, the core writes bar, which will be placed at the tail of the write buffer. So if the core has a non-merging write buffer, the writes will occur exactly in thread order. On the other hand, if the core supports a merging write buffer, then each entry will correspond to a cache block, and there will be valid bits for every word in the block. Now the core writes foo. As the memory allocation table shows, foo corresponds to the first word in the memory block that starts at address 200, so it will be placed in the merging buffer as shown here. Next, the core writes A. A corresponds to the first word of the memory block that starts at address 400, so it will be placed at this position in the merging write buffer, and only that valid bit will be set. The third write in thread order is the write to flag. Since flag is allocated in the same memory block as foo, flag will be placed at this position in the merging write buffer. Oh, Houston, we have a problem. The topmost entry of the write buffer will normally be written before the second entry. So the write to flag will actually take effect before the write to A. This is exactly what we did not want to happen. To complete this example, the write to bar will be placed at this position in the merging write buffer and will be written together with A. Here's another example. Threads T1 and T2 do not want to be in their critical sections at the same time. They try to accomplish this using a pair of warning flags. Thread T1 sets its flag, flag 1, to indicate that it wants to enter its critical section. Symmetrically, thread T2 sets its flag, flag 2, to warn thread 1 that it wants to enter its critical section. The question now is, can both if statements evaluate to true? In other words, can both threads enter their critical sections at the same time? Well, if writes take effect and are observed by other processes immediately, then this is impossible. However, if the write invalidations are delayed and the old value is read, then unfortunately it is possible. Before we consider a parallel memory model, let's try to define the sequential or uniprocessor memory model. What is the implicit assumption we make about the order of reads and writes when we design or program a sequential uniprocessor? The uniprocessor memory model is memory accesses are atomic and occur in the order specified by the program. This implies that this property is always maintained. A load always returns the value written by the previous store to the same memory location. Whatever we do in hardware or software, out of order execution, write buffer merging, instruction reordering, etc., we make sure that this property is maintained. As this example shows here, the read of A always returns the value written by the write of A, and the read of B always returns the value written by the write of B. So, why don't we adopt this beautiful, simple to understand memory model for multiprocessors as well? The problem is there is no global order of reads and writes in a multiprocessor. The read of this A here in thread T0 may return the value written by the same thread or the value written by the other thread T1. Furthermore, the program has to be correct in all cases. So we conclude that the uniprocessor, the beautiful, simple to understand sequential memory model, cannot be adopted for parallel processes. This concludes this lesson. Thanks for watching. In the next lesson, I will describe sequential consistency, which is the most intuitive memory consistency model for multiprocessors. Hope to see you back.